What do you I had x squared plus 4y squared times x squared minus 4y.
Well, you can't just do that.
I had 5x minus 6y.
Well, you can't just combine the two. You have to have them out like this.
Yes.
I didn't know what it did. But I didn't know what it did. Oh, yeah. Oh, that is the. I didn't really. I think it was.
All right, what are some things we came up with here? Well, in part A, if I'm going to simplify that, we kind of got lucky on this one because when I break it into the two parts, because again, really, if I'm doing the square root of this, that's the same thing as taking the square root of the top, square root of the bottom. And this was nice because they're perfect squares. So what was our simplified answer? Yeah, just 5/3. Okay, so if we're lucky enough to have perfect squares, then we just got to square root and see what we get. The second one, we were kind of lucky. Was one of those perfect squares? Yeah, the top one was, right? But the square root of 7 is not a perfect square. So I'm going to leave it alone and have it look like that. Now, in the past, when I'm talking in the past, I'll say when I was in high school, so we're really talking in the past now. But anyhow, before calculators were prevalent and used as much as what we use them now, a lot of times we rewrite this a little bit more. We would do what's called rationalizing the denominator. And what that means is we wouldn't want a square root in the denominator. So we wouldn't leave it like this necessarily. We'd try to get rid of that square root in the denominator. So here's another way you may see this answer written. If I want to get rid of the square root, well, one way to get rid of the square root is multiply it by itself. So if I were to multiply the bottom by the square root of 7, I know the square root of 7 times itself just gives me a nice, neat 7. However, if I did that to the denominator, I'd have to do that to the numerator. So another way I might write this is 1 times the square root of 7, or just the square root of 7, and the square root of 7 times itself is 7. So you might see it written like this, but you might also see it written like this. I don't care which way you wrote it. Okay, if you wrote it like the first one, that's okay. How can I get away with this? How can I get away with multiplying it? Wouldn't that change the value? Yeah, because the square root of 7 over the square root of 7 is 1, and if I know if I multiply it by 1, I've kept the value the same. All right, but this would be called rationalizing the denominator. I'm not necessarily concerned with you doing it that way, but if you had that problem and you like checked your answer, it may be written that way. Okay, but it really means the same thing. All right, what about the last one? Last one on the top of it. There we go. All right, what about this last one? How do you attack this one? Okay, who would you guess?
I like set it up by 2 plus radical 3 times 2 plus radical 3, like a. You know what I'm saying?
Okay, so since we're squaring it, we're really just multiplying by itself. All right, how'd you go from there?
And then I just multiplied it and got 4 plus 2 radical 3 plus 2 radical 3 plus 3.
Okay, and so what do you get for an answer?
7 plus 4 radical 3.
Okay, so good, that's the correct answer. All right, so you just thought about multiplying it out, maybe foiling it if you thought about it doing it that way. This one, you could also, if you're more comfortable with generic rectangles, you could have set those up. You could have said, well, I've got 2 plus the square root of 3 and 2 plus the square root of 3, and then attacked it because 2 times 2 is 4. We've got 2 square roots of 3 twice. And I got the square root of 3 times itself, so that's just 3. And then put all that together. All right, so that's really no different than if it said x plus 3 squared. You would attack it the same way. The big thing there is, remember, whenever we have the square root times itself, it wipes the square root out. All right, so I gave you that because you're going to see some problems pop up in your homework here in the next few lessons where they throw some of those things out at you. What about our factoring? Let's start with what we're hopefully comfortable with. Let's actually start with the last one. That one we know if you wanted to, at least you could set up your generic rectangle and attack it that way. If you did attack it that way, our goal would have been trying to multiply to get negative 24 and add to get negative 5. So what do you use if you did that? What can I multiply to get negative 24 but add to get negative 5?
Negative 8.
Okay, negative 8 and 3. So if I filled those in, you can try to factor it that way because 3x squared and 3x have a 3x in common. And if it's 3x here, I need x here. What will go down here? 1. And x times negative 8 will give me negative 8x. So when you factor this one, you should have factored in the 3x minus 8 and x plus 1. Okay, so hopefully that one we got because we've been doing those for a while. The other two are a little different though for a couple reasons. We only had 2 terms. That was one thing. It actually had 2 variables as well. And so far when we factored, usually we've only had either an x or a y or something like that. We haven't had both. So let's see, could I use this same method and try to come up with the factored form for this example? Well, let's say I try to use the same method. Say I like the generic rectangle idea, so I made my rectangle. I did x to the 4th in one of them. I did negative 16 y to the 4th in the other one. And I know my goal is, I'm going to multiply those 2 together, first of all. But usually I look for the term that I haven't listed. Like here, we listed looked for the negative 5. But I only had 2 terms there. So what would be the value of the third term?
0.
Yeah, 0. So I'm looking for something. What can I multiply to get negative 16 but add to get 0? What can work for that?
Negative 4x squared y squared and 4x squared b squared.
Right. And we had to use x squared, y squared because I know when I multiply them together, I needed those 4 powers, right? So I could put one of those up here, negative 4x squared, y squared. The other one down here, positive 4x squared, y squared. All right, let's see what we got when we did that. Well, if I look at these 2, they've got an x squared in common, which means I'd have an x squared here. I'd have to figure out what times x squared gives me that. Well, that's going to be 4y squared. I'd have to figure out what times x squared gives me this. Well, that would be negative 4y squared. And 4y squared times negative 4y squared gives me that, so it seems to work out. So here's what I ended up with. I ended up with x squared plus 4y squared and x squared minus 4y squared. So it was doable with the generic rectangle. Did I need all that though?
I'm not sure, but can you factor that further?
Yeah, good question. I'm going to come back to that here in 1 second. Though. You're right. We can go one more step. But let's think about these two terms here. They worked out with that generic rectangle. We kind of had a lot of stuff going on there. But is there anything that I would notice from this original to now these two terms? Anything that jumps out at you there? Yeah?
Well, which one is perfect square?
Okay. So we know we could have 4 and 4 since it was a perfect square. All right. So that's one thing that jumps out. Anything else that jumps out at you?
If it's a perfect square and you put a plus on one side and minus on the other, then it makes it so you get rid of like the middle number.
Okay, and that's why we only had 2 terms instead of 3. All right, so we had a subtraction sign there, which means I needed a plus and a minus. Ben said 16 was a perfect square, so I have a 4 and a 4. Is x to the 4th a perfect square? Yeah, because we got x squared and x squared. Y to the 4th is a perfect square. So that's why I have y squared and y squared. So really what I had 2 perfect squares that were being subtracted. And anytime that happens, that's referred to as a difference of squares. And the nice thing about a difference of squares is the factors would be those square roots with opposite signs. In other words, the square root of x to the 4th is x squared. The square root of 16 is 4. The square root of y to the 4th is y squared. And then all I had to do was change the signs on it. Now, let's go back to AJ's question. Could I keep going? Well, do I have another difference of squares with those 2 factors? Yeah, the second one, right? The second one, this is a perfect square. This is a perfect square, and it has subtraction. So I actually could have broke that down into x plus 2y, x minus 2y, because those would be the square roots with opposite signs. Could I do that here? These are both perfect squares. No, I can't do that because it's addition instead of subtraction. So if I were factoring that out completely, I'd actually have 3 terms. So the second one, is it a perfect square or is it a difference of squares? Yeah, we got 25, so we know that's 5 and 5. We got x squared, so I know that's x. I've got 36, that's 6, y, and 6y. One of them has to be positive, one of them has to be negative. Can I keep going on that one? No, that's as far as I can go. All right, so you're going to see some pop up where you have difference of squares versus like our traditional, here's 3 terms that we're going to look at. All right, so kind of some new stuff on that. Well, here's what we're going to do today. And for what we're going to do today, you're going to need, initially at least, a graphing calculator. But we've done all this stuff with functions. We've been moving them around. We've been stretching them, compressing them, all that sort of thing. And we said all these things that we changed on the equation kept working for every single equation, whether it was y squared or x squared or x to the 3rd, 1 over x, etc. What we're going to look at today is, well, what if I don't have a function? Can I still move something around that's not a function? So here's the first thing I want you to do, is I want you to see if you can graph this equation. Now notice this equation is a little different than normal because it's an x equals equation. So what that means is you're going to have to do a little rewriting if you're using your graphing calculator. If you want to use Desmos, that's fine. If you use Desmos, the advantage is you don't have to rewrite it into y equals. Okay, but if you do it on your calculator, you're going to have to rewrite that into y equals. But here's what I want you to do. I want you to graph it, and then I want you to see, well, what might be any key information about that graph? What might be some things we'd look for on that graph once you've made the graph? Okay? So go ahead and start with that. Again, you can use your calculator, you can use Desmos, either one. What would my equation be if I made a y equals equation? Okay. So those of you that put it into the calculator, you got that graph? If you did Desmos, is that what yours look like? No, what yours look like?
It's a parabola, like a full parabola.
Yeah, it had not only the top side, but it also had the bottom side. Well, how could I maybe make sure that's showing up on my calculator? Not quite. We still want to think in terms of the square root part. We got to think of something else.
The absolute value of x?
Absolute value of x, remember, is going to give us a V shape. So that's going to change the shape.
In the thing, so it's like always positive. So we could like,
Well, what are we missing though? Like, what did you do Desmos?
yeah.
Which part of the graph am I missing right now? The top part or the bottom part? The bottom part. If I did absolute value, it's going to stick to only those positives. When I take the square root of a number, say I did the square root of 25, what are my options for that answer? I could have 5 or I could have -5, right? So I've got to think about both sides of my graph. So I'm going to have to put in a second equation where I do the opposite of the square root of x. And now I get what you were getting on Desmos if we tried that. So I do have this parabola. A little different than our other parabolas. Our other parabolas went up and down. This one's going left and right, it looks like. And when that happens, when we have a parabola that's on its side here, that's what the book is going to refer to as a sleeping parabola. So I don't know how technical that term is, but that's what they call it, a sleeping parabola. Why is it a sleeping parabola? Laying down, right? So the parabola is laying down, so that's why it's a sleeping parabola. Well, what might be some key points for our sleeping parabola? The origin is because it's our vertex. All right, so just like a regular parabola, our locator point's still the vertex and it's still right now at 0, 0. What might be some other things we look at? The y-intercept might be important. In this case, it happens to be at that same point, right? What are some other things we looked at parabolas in the past that we wanted to see if, eventually we make some changes? Yeah, wider or narrower. Okay, so here in a second, we're going to try to figure out how to do that. What was something else that we paid attention to? Stretch or compress. So we'll figure out how we can do that. What was something else we paid attention to? Say again, sorry. Okay, if we moved it left, right, up, and down, that was something else we looked at. What was the last thing we looked at with regular parabolas? Yeah, if it was opening up, opening down, right? So some of the things we'll look at with sleeping parabola, we'll still look at that stretching, compressing part. We'll still look and see, did I move it around? And I'm still going to look and see, not if it's opening up or down, but now whether it's opening to the right or to the left. So here's what I'm going to have you do. First of all, I'm going to have you move into your groups. And once you're into your groups, I'm going to have you see if you can figure out how to do these changes. One thing I want you to do is I want you to figure out how can you make the equation change. So in other words, we go back to this one still. But how can I change that equation in order to have that parabola open left instead of right? The second thing I want you to do is how could you change that equation to make the vertex be at -1, 3 instead of at 0, 0? And lastly, I want you to decide what would this do to my graph as far as the shape of the graph itself, okay? So figure out an equation that would make it open left, then start over, figure out how could I change that original equation to have the vertex there, start over again, and figure out what's happening in this equation here. All right, so go ahead and scoot into your groups if you would, please. We did groups the other day, didn't we, with our new groups? Yeah. Okay, so go ahead and scoot together. Feel free to test it out on decimals if you want, or your calculator.
You just make it already, and the first one you just make it.
The same as the
first one, the second
It's tough to do X equals negative y is negative.
And then for the second one, you should do like x equals, radical x plus 1 plus 3.
Inside the parentheses, you put y minus the you do minus the y value.
So when you're making the changes, again, always go back to your original, your x equals y squared equation.
X equals a y minus 3.
Oh, yeah.
No, but how do you get? I know how to get the
Oh, I don't know. Yeah, what is, I was running around to get it down.
So how did you get it today? Why I did that? Yeah. Slightly different. Y minus 3. Yeah, one x squared. Oh, y squared minus 1. Yeah. Let's go back to our original since you kind of have an idea of what to do.
I got the second.
Let's go back to the original one. Go with the biggest one.
Second one, I got y is equal to, I got like
3 up there.
and then plus
Which value?
and y
The y value. I would make sure to take care of the y value before I square. You put it in the parentheses. The y and the negative 3. Okay. Yeah, what he did was he said, I'm going to do y minus 3 in parentheses before I square. Okay, so I took care of it up. So it's really the same idea we had earlier, except we used to have x instead of now we have y. We used to have y instead of now we have x side multiplied. It's retraining our brains going out.
So number 3,
Yeah, I know.
I get a.
It's like negative y squared minus 1. That's on that. That's negative 1.
Okay, some of these were easier than others. What about the first one, opening left? Did this group figure out how you can make it open left?
Do x equals negative y.
Right. Probably what we would expect. To make it do the opposite thing, we just change the sign. Make it x equals negative y squared. All right. Vertex at negative 1, 3. Did this group figure out a way to do that?
We have y equals radical x plus 1, and then plus 3. Or then y equals negative radical x plus 1.
Okay, so you did both sides. All right. Let's see if we can rewrite that a little bit where we stick to an x equals situation. All right, so this is the right idea. How can I rewrite that but have it to where it's an x equals situation? This group come up with something?
We had x equals, in parentheses, y minus 3 plus parentheses squared minus 1.
Right. And if I started with this equation, I could get to this one because I could subtract 3. That would give me the y minus 3. I could square it to get rid of the square root. And then I could subtract 1 to get x by itself. So if I stuck to the idea of x equals, this would be my equation. Now notice what happened. It was almost like what we did with the other parabolas, except with the other parabolas, we started out with this general equation, where we had a x minus h squared plus k. Remember, we did that a lot. So we had the x value inside the parentheses. Well, here we have the y value inside the parentheses. Did subtracting do the opposite of what we thought it might do? Like if I did x minus something here, what did that do? It moved it which way? Which one would it be if that were, say, x minus 3? To the right, okay? Well, this was y minus 3, and it moved it up, okay? So it's still gonna have that same effect to it. Then we used to move it up or down by this value when we had a y equals. When I have an x equals, this is going to move it either left or right. In this case, to the left. So it's kind of retraining our brains and just flipping those two things around. What do you think is going to happen on the last one? Well, when you did x equals 3y squared, did that create something that was wider? Did that create something that was narrower? Yeah, it was narrower, okay? Which sticks to what we usually have, right? But when you think about that narrow stretch, because we're still stretching it, did we still stretch it this direction? No. We stretched it this direction. So it is a stretch, but it's actually a horizontal stretch versus the vertical stretch. And that's because the graph's not going vertically anymore, the graph's going horizontally. But it's still making it thinner, it's still making it going to be a little bit thinner than what it was before. So a lot of the stuff stays the same, but some of it is changing. So our equation for a sleeping parabola is going to look very similar to what we used to do when we had our regular parabola, with a few slight changes. So here's how you usually see the equation written for a sleeping parabola in general form. It's an x equals instead of a y equals. You're going to see b used instead of a because we're not doing a vertical, we're doing a horizontal stretch or compression. We have y minus k now squared plus h. So the vertex is still at hk, but the location of those two things are different. So the x value of the vertex is here, the y value of the vertex is here. So if I gave you this equation and I asked you to describe it, if I said, where's the vertex of this located? Where would the vertex be located? What would be the x value, first of all, of the vertex? Be careful, because that's the negative 1's part of it, but that's for, yeah, the y value. what would the x value be?
Positive or negative?
Negative 3. So the vertex would be at -3, -1. Would this one open to the left or open to the right? Open left, open right.
Right.
Not quite. Left, because we got the negative out front. Is this horizontally stretched or compressed? What's this tell me? Stretched. Horizontally, it's stretched. Just like it was stretched before when we looked at the vertical. Okay. All right, so again, retraining our brains a little bit. We won't do a ton with sleeping parabolas, but if they do give you the equation, I would expect you to know how to pick out these 3 things or know how to sketch it on there. Okay. I mentioned the fact that it's not a function. What's that mean? When I say it's not a function, what am I saying?
That each like x doesn't have its own y value.
Right.
So, like 2.
If I looked at this x, there's actually 2 outputs. It's got 2 y values. So that means it's not a function. Or if I think about the vertical line test that you may have learned, if I took a vertical line here, I'm going to hit it in 2 spots. And if it's a function, I should never hit it in 2 spots at one time. So this is one example of a non-function. And with that non-function, we kind of did the same thing with our shifts, but they were slightly different on this one. But we still kind of had the same idea as far as we can shift it around by doing some adjustments to our original equation. We're going to do one other non-function today, and we're going to see how we can move that around as well. Now, for this investigation, Desmos is probably going to be your best option. You can do it with graphing calculator, but Desmos is going to be easier. All right, so the function you're going to be working with here starts out with this equation. X squared plus y squared is equal to 9. Now, I'm going to change the directions on here a little bit because, again, I think Desmos is a better option than using your graphic calculator. So don't worry about solving for y on this one. But I do want you to find the graph on Desmos by using that equation. And then answering those questions after that. After you finish number 4, I'd like you to stop. Okay, so when you finish number 4 within your group, stop and tell me, and I'll check your answers to make sure you're on the right track. And then I'll go on from there. So stop after you get to number 4. Don't worry about solving for y in number 1. Just go straight to making the graph. And again, Desmos is the best option. When you finish number 4, as the group tell me, I'll come look and make sure your answers are correct. They were looking at-
Like these two. Based on the results, you can try to find out where the center of your radius is, just like the result without that. And then once you do that, you have to check.
Yeah.
So now we can see how we can move this around. So you can solve it.
Make sure we're done.
Alright, so what you're doing now is, again, worry about solving. Pick out the 62 information. Based on your results, you see if you can figure out the backside without the rest of the
I'm done.
and then you can check it out. Good. Alright, so now you're gonna enter this in, don't worry about solving for. Enter this in, you see what the graph looks like. Pick out the information, and then see, if you can use these results to figure out on this side where the center and what the radius is without graphs. And then you can check your answer after that. Same thing. You're gonna graph this, don't worry about solving, graph this. Pick out your information. Then based on the results here, you're gonna see, could I pick out the center radius of these two without graphs? Okay, and then test it out by the president without graphs.
Yeah.
Alright, so now again, don't worry about solving that. Enter this in with the graph. Pick out your two pieces of information. And then based on the results that you get on this side, you can kind of see on the back side. Could I pick out this center radius without graphs?
Okay.
Thing that I like.
Yeah, what you get for your center?
And, yeah, we are, we're right.
That's right. And then two for you. People were going
Well, we're right.
Imagine.
I think it's half of the last, or no, the last number is square root. Like square root of the
Yes.
How can you guys get that stuff? I don't like it. If you don't start it, you can do it.
Oh, wait, never mind.
Maybe like that weird fire system.
It's always like.
Make sure you test it out after you label your center and radius, see if it really matches what you think it's going to be.
Maybe like.
All right, so we're looking at the equation of a circle here. That was our non-function. Notice one thing, with the equation of a circle, you're going to have an x squared plus a y squared situation. And those will both be on the same side. So anytime you see an x squared plus y squared, or any variation of that, but they're on the same side, that's going to be considered a circle. So this was the first example that everybody came up with. And then we have the two on the back. So somehow we're trying to figure out what's going on here to where I can just pick out the center and the radius without actually graphing it. Because if I ask you to graph a circle, you need to know where the center is, you need to know how long the radius is. If you know those two things, you can graph it. So the first one, x plus 5 squared plus y plus 3 squared equals 16. This group here, what did you get for your center point?
-5.
Good, -5, -3. What did you get for your radius? 4. Good. All right. -5, -3. How can we pick out those values? How could I get the -5? How'd you get it?
Since 5 is being added to x, we can just take it and get it the opposite side.
Right. It's inside the parentheses, just like all the other graphs we've done. Inside the parentheses, we think in a lot of ways how do we get to 0, or what's the opposite? In this case, -5. This one's inside parentheses, so it's got to be -3. So that means on this one down here, you should have had a center point of -7, +1. What about the radius? How do we get the radius from our equation with this group?
We take the square root of the last number.
Yeah, whatever our constant is, in this case it's 16, we take the square root. So over here we have 25, so when I square rooted that, you should have had a radius of 5 on that. All right, so our other non-function, our circle, we should be able to pick out the center and pick out the radius, those two things, okay? So we got two non-functions. We've got the sleeping parabola, and we have the circle. And we'll deal with those two things just like we do our regular functions. All right, two things that I want you to do. One of them needs to be done before you leave. The second one will be your assignment for Monday. I'm going to put up 3 different things up here. And this is going to be kind of your exit ticket for today. This is something I need before you leave. The first one is I want you to sketch this graph. Second one is I want you to write the equation of a sleeping parabola that does this. That's true. That opens left. The vertex is at 4, -5, and it's stretched horizontally. By factor of 5. And then the last thing is I want you to write the equation of a circle where the center is -1/6 and the radius has a length of 7. Okay, so those 3 things there I'd like you to do. Do it on a separate sheet of paper because I'm going to collect those before you leave. And then your assignment I'll put up here, and it'll be due on Monday.